Welcome to this next lecture on vibrations of plates and shells. Now last time we looked at the Rayleigh quotient and we said that it gives an estimate of the fundamental natural frequency of a system. In the 1 degree of freedom case, it actually exactly gives the 1 natural frequency. So let us see what it does for a 2 degree of freedom system. So here is a 2 degree of freedom system. This mass is 0.2 kilograms, that is 0.3 kilograms, and let us say this is my first mass. So its displacement is u1, and this is the second mass, its displacement is u2. Okay, and this spring, let us say, has 100 newtons per meter, and this spring has 200 newtons per meter. Okay. So now let us say they are vibrating in a mode, Okay. Then what happens is, what is their relationship? u1 will be given by some amplitude sine omega t plus alpha, and u2 can be given by some other amplitude sine same frequency, same phase. Okay. So u1 and u2 can carry some sign. So then what is u1 dot? u1 dot is omega times u1 hat cos omega t plus alpha, and u2 dot is equal to omega u2 hat cos of omega t plus alpha. Okay. So now what is the maximum potential energy? V max is given by 1/2 the maximum stretch in this spring, which is 100 into u1 hat minus a 0 whole squared. This end of the spring is into the wall, plus 1/2 into spring constant into u2 hat minus u1 hat squared. Okay. Then we have the kinetic energy total. Okay, total kinetic energy Tm is 1/2 m 0.2 v square, which is omega square into u1 hat square, plus 1/2 0.3 omega square u2 hat square. Okay. So now if we say that the conservative system vibrates such that the maximum potential energy is equal to the maximum kinetic energy, we do this, what we get is 1/2 100 u1 hat minus 0 squared plus 1/2 200 u2 hat minus u1 hat squared, that is equal to 1/2 0.2 omega square u1 hat squared plus 1/2 0.3 omega square u2 hat squared. Okay. So now if we separate omega square out, then I have, okay, if I keep separate omega square out, I have 1/2 100 u1 hat minus 0 squared plus 1/2 into 200 u2 hat minus u1 hat whole squared, okay, divided by 1/2 0.2 u1 hat squared plus 1/2 0.3 u2 hat squared. This we call the Vm, this we call the psi m. Okay. Now if we say that eta is the ratio of u1 hat by u2 hat, okay, then what happens here? This ends up looking like omega square is equal to 100 eta squared plus 200 1 minus eta squared divided by 0.3 plus 0.2 eta squared. Okay. Now if we find out separately the exact natural frequencies, then they are omega 1 is 12.91 radians per second, and correspondingly the u1 hat by u2 hat is equal to 0.75. Okay. And omega 2, the second natural frequency, is 44.72 radians per second, and the corresponding u1 hat by u2 hat is -2. Okay. So now so you can say that this is a mode shape. This is a mode shape. Okay. So if you substitute the correct mode shape, okay, substitute the correct mode shape, then you will get the right value, which is 12.91. Okay, omega 1 you will get 12.91. And what is the correct mode shape? It is 0.75, eta equal to 0.75. If you substitute any other value for eta, any other shape for eta, any other value for eta other than 0.75, then you will get a omega 1 nu which is greater than omega 1. Okay. So the value is bounded by omega 1 on the lower side. Okay. So you can kind of see for various values of eta what is going to happen. Okay, if let us say eta is 0.7 over here, you take all other values and you approach 0.7, again beyond that it will go up, eta equal to 0.75. Okay. So we will for now say that this Rayleigh quotient gives Rayleigh quotient is bounded on the lower side by the correct or exact natural frequency. Okay. So let us show this in some manner. Let us prove this in some manner. So if I say okay, let us go further and use the fact that the second natural frequency is 44.72 and the corresponding eta is -2. Okay. So the general displacement now can be represented by some g1, a constant 0.75, 1.00 plus g2 minus 2.0 and 1.00. Okay. So here if I choose g1 is equal to 1 and g2 as 0, then I get eta as 0.75 and I get omega is equal to my omega 1, which is 12.91. Okay. If I choose any other value, that means some value for g1 and some non-zero value for g2, then what do we get? Okay. So now let us see, if we now substitute this into my Vm and psi m from above, I get for Vm 1/2 into 100 into 0.75 g1 minus 2 g2 whole squared, okay, plus 1/2 into 200 into 0.75 g1 minus 2 g2 minus g1 plus g2 whole squared, which can be further simplified to 1/2 into 100 into 0.75 squared plus 200 into minus 0.25 squared into G1 squared plus 1/2 into 100 into minus 2.0 squared plus 200 into minus 3.0 squared G2 squared. Okay, that's what we get for Vm. Then for Tm, what do we get? The kinetic energy function, what do we get? Oh no, I'm sorry, the total kinetic energy, what do we get? Omega square by 2, 0.2, 0.75 G1 minus 2.0 G2 whole squared plus omega squared by 2, 0.3 G1 plus G2 whole squared. Okay, which if we again bunch G1 and G2 separately, we get omega square by 2, 0.2 into 0.75 squared plus 0.3 into 1.0 squared G1 squared plus omega squared by 2 into 0.2 into minus 2.0 squared plus 0.3 into 1.0 squared into G2 squared. Okay. Now if we equate Vm to Tm, Vm equal to Tm, then we get omega square is equal to 100 0.75 squared plus 200 into minus 0.25 squared G1 squared plus 100 into minus 2.0 squared plus 200 into minus 3.0 squared G2 squared divided by 0.2, 0.75 whole squared plus 0.3, 1.0 squared G1 squared plus 0.2 minus 2.0 squared plus 0.3 1.0 squared into G2 squared. Okay. And this, okay, this can be written. So there is a certain number multiplied by G1 square, certain another number multiplied by G2 square, again in the denominator a certain number multiplied by G1 square and another number multiplied by G2 square. Okay. So this we will write as equal to K1 G1 square plus K2 G2 square divided by M1 G1 square plus M2 G2 square. Okay, and we will call K1 K2 as generalized stiffness, and M1 and M2 as generalized mass terms. Okay, related to the first mode and second mode. Now if we select G1 is equal to 1 and G2 is equal to 0, then we get omega 1 square, which is K1 by M1, or K1 is omega 1 square M1. Similarly, if we select G1 as 0 and G2 as 1, okay, then we get omega 2 square is equal to K2 by M2, okay, such that K2 now is equal to omega 2 square M2. Okay, so now this can be written as, okay, M1 omega 1 square G1 square plus M2 omega 2 square G2 square by M1 G1 square plus M2 G2 square. This is omega square. Okay, now let me do it on the same page here. Okay, so now if I divide both sides by omega 1 square G1 square, then I get on the left omega square by omega 1 square G1 square is equal to, in the numerator, M1 plus M2 omega 2 by omega 1 squared G2 by G1 squared divided by M1 G1 square outside plus M2 G2 by G1 squared, and this goes. Okay, so I have omega square divided by omega 1 square given by M1 on the top and M1 in the denominator plus M2 on the top and then M2 in the denominator, G2 by G1 squared, the same G2 by G1 squared. So far we are okay, but on the numerator we have omega 2 by omega 1 squared, and omega 2, the second natural frequency, is greater than omega 1, and therefore omega square by omega 1 square is greater than 1, okay, or greater than equal to 1. Okay, when is it equal to 1? If G1 is taken to be 1 and G2 is taken to be 0, okay, if G1 is taken to be 1 and G2 is taken to be 0, then you will get the equality sign, okay. But if you take any other value, what this is going to do is it will be greater than 1. So what the estimate you get is going to be greater than the actual value, okay. So this method of finding the natural frequency, okay, this method of finding the natural frequency by assuming a mode, and taking the ratio of the potential energy and the kinetic energy function and finding the natural frequency is called Rayleigh's method. And this expression is called the Rayleigh quotient. It's called the Rayleigh quotient. Okay. Now what next? The next thing is that, see, we have only been able to show that if you get the exact mode shape, you get the fundamental natural frequency. Okay. If you do not get it exactly, if you get an approximate, then you get something greater than the fundamental. Okay. So we do not, that is all we have got, okay. We do not know where the other frequency will be in relation to the actual second natural frequency or the third natural frequency and so forth. All we know is that if we are not exact in terms of the first mode, then our estimate is higher than the actual value, okay. Now the approximate mode shape must have some valid property. If we do not know the exact mode shape and we are going to approximate it, it must have some property for which it is a valid candidate. Such a candidate is called an admissible function. Okay. An admissible function is a function that does not violate the geometric constraint of the system. Okay. That means you can give the system an initial displacement in this shape. Such a shape is called a admissible function. Okay. Now we are at the end of our time. I will close the lecture here. We will continue from here in the next class.